Hey guys, and welcome to another Thoughts on video, where I've already covered the RX Vega, kind of. I mean, it was very ad hoc. This is also going to be ad hoc, but today, for I wouldn't say unbiased, but for fairness, we're going to be covering. Um, I'm going to be focused on the new Volta architecture from NVIDIA. And I couldn't sleep last night, so I spent most of it just going through the couple of blog posts that they've put up about the architecture, what they're sort of looking to achieve with it, and stuff like that. And to begin with, because they've always showcased, uh, because since they've showcased it, and they were like, well, this is how it works, and it looked really interesting because it looked like what they were doing was like a 3D transistor. And they'd been showcasing that data goes this way, and then data goes this way, and then it all gets processed this way, which is really freaking cool. Like, I thought this was like some sort of groundbreaking, amazing thing that they were showcasing, and no, it's just a data visualization. Um, it's uh, it's kind of like sort of being really excited for, I don't know, like some sort of toy at Christmas, and then you open it up and you realize like it doesn't do jack that like the adverts were saying it was going to do, and you're just like, oh well, and oh. Okay, so obviously one of the big things that they're pushing here is like the relative performance to Pascal. So I don't even remember what DGM is, but the fast Fourier transferring, which is used in a lot of 3D aspects, they're saying is like 1.7 times, and then CUDA physics is 1.5 times, and then data streaming is, you know, the same sort of 1.5 times. And you're like, okay, this looks kind of impressive, especially when they're saying, well, we can get 120 teraflops from this thing, and you're just like, my God, that's powerful, and it is until you actually realize this. Matrix, multiply, and accumulate. Now, for those, I thought, oh well, this is just like it's going to get up to 120 teraflops with matrix multiply and accumulate. It's not, obviously it's going to have similar sort of capabilities as your standard floating point 32 thing, but no. So what a matrix, what the multiply and accumulate is better known as is this. It's better known as the fused multiply and add. Or I suppose because it does it the other way around, the fused add and multiply, but that probably doesn't have the same quite ring to it. So what a fused multiply and add is, and hey, where's my images gone? Can I? Okay, if I do that, will you give me all my pictures back? Yes, you will. Okay, so this is what a fused multiply and add is. So this is being multiplied. So this matrix is being multiplied by this matrix, and it's being added to this matrix, and then this is our result. It probably should be arrows the other direction. As I said, it's confusing because of the way they say it. That's actually the multiplication thing. It's confusing the way they state it because the direction's actually that, and then it's giving the result. But basically, this is all it does. This is all the Tensor Core is capable of. This one mathematical equation. That's it. It can't do anything else. It's a one-trick pony. And in this one trick, it is actually very, very powerful because of how it's doing it. So, I mean, not to take away from like it being kind of cool. So normally speaking, we wouldn't have this. So the standard fused multiply and add is only working on a single vector at a time, and this would be doing that through a simmed instruction set. So we'll come down here. So you know you'd have your single whoop, I forgot to turn on drawing. So like you'd have your single one of these, and it'd take also from this. So you'd have your two registers. They'd come out to the fuse multiply. So you'd have, what is it? R1 plus R2. Gonna multiply it by R3. And then the result will go down there. And it is faster. Like, it is faster for what you're trying to do. So rather than the reason, oh shit, wrong thing. The reason it's faster is because rather than doing like each of these individually, which would require, what is it, 4 times the calculations, because you're doing an extra 3 sets of calculations. And by the way, this is how they're figuring out the whole 12 times performance increase. So you would be sort of going along the lines of saying, well, this is 1, 2, this is 3, this is 4, 2, 3, 4, 2, 3, 4, and so then you'd be doing the calculations in order. So you know, and then you know you'd be yeah, I can write. I can. I swear. Oh god, that's just messy as hell. Yeah, so like you'd have your return equals a times B plus C. And so, like, you'd be running through this calculation 4 times instead of 1 times. So, you know, you're doing like 4 calculations where 1 would work. And then obviously what we've got here is, because it's a matrix, it's a 4x4 matrix, you're saving even more. You're saving even more performance. So again, like, you're performing it at 1 over 4x4. So it's saving what, 1 in 16th performance. And a good thing to keep in mind. A good thing to keep in mind in regards to this is that while you're saving a 1 in 16th, actually no, we're operating on 4. So, because you're operating on this on sort of like one operation for every 4x4 operations, it gives the illusion that you're doing a lot more processing. You're doing you have this much greater, what was it, 120 teraflops of performance, when realistically, actually, sort of, you know, in terms of actual calculation, of course it's going to be the wrong bloody thing. You're actually at 7.5 teraflops. Like, that's the actual teraflop performance that you're putting through. And if you notice, we come up here, 7.5 is the 64. Is the performance of that. But it gives the illusion of, you know, being capable of doing 120 teraflops of performance. And it's all because, like, you're doing a single operation where normally you'd want to be doing 16. And I mean, it's the same as, like, if you were to be doing, if instead you were doing like the individual operations like that, rather than like the combined operations. So I mean, here, like, you've got the 4 operations normally, whereas here you've got 2 operations. So that's all that's going on. And yeah, as a note, you're also taking into consideration like the copies, like, to and from memory. That can be our memory for now. And yeah, so the way that they're calculating a lot of this is because the tensor cores are broken down into matrix blocks. these are each one of these are obviously a 4x4 matrix. And that's made up of all of these. So that's one set, second set, third set, fourth set. So if we the FP32, and we've got set 1, set 2, set 3, set 4. Well, then each one of those equals a single equals one of those, and then we have 8 of those. So you know that's sort of how many technically, and this is the important thing to keep in mind here. Technically, there's 8 of them. However, because you're using them in 2 groups, because you have to, you have to use those 2, those 2, those 2, those 2. Because you're using them in groups of 2, as what's happening is, you've got register 1 there, and then this is multiplied by register 2. This is then stored back into register 1, and then register 1 is added to register 2 again, which has all new data in it. And so, what is it? You're doing 1 multiplication operation, then a load store operation, and then another load store operation for the new data, and then 1 add operation. And so, like, you've got 4 operations that are going on, but you'd still have like those 4 operations even if you were sort of like doing these like the individual, which that was just messy, just sort of how it's going down. So I mean, it's great because, I mean, you can get quite a substantial performance increase, but it's not very good for like practical gaming applications. The one thing, I mean, it'll be great for like physics, but I don't know how much they're going to focus on physics. So now, one thing I find interesting is we now have separate pipelines. So I'd imagine, because this is like the Volta workstation card, I'd imagine they won't have this for the actual gaming card. And in fact, there's very little point to actually having one of these tensor cores. Like, 1 tensor core will probably be useful, because that provides the ability to have like a single 4x4 matrix multiply. So this could be very, very useful for 3D transformations. So it could allow them to have a higher throughput of geometry, like higher tessellation and stuff like that. But realistically, the bulk of what we're working with here is these right here. They're basically the bulk of all of this. In fact, if I get a nice color, not a nice color. Oh, well, the highlighter sucks. But yeah, I mean, like, this is realistically what we're going to be using for like actual gaming. And then these will just be, these are unimportant. And as I said, I think one tensor core can be quite easily just removed. So it should save an awful lot of space per CUDA core, but whether that's the approach they actually take or whether they just sort of disable them, I don't know. I think it's more likely that they'll just disable them rather than having two SKUs. Now, one thing that's interesting is they're going down to 12 nanometers. So this means you have plus 25% space for, you know, compute. So plus 25 millimeters squared and minus 25 power. Which, by the way, is how they're keeping 300 watts with that. Still, what this ends up meaning is that because they're not going to go over 610 millimeters squared, and I'll explain why in a second, that will not be that. That will instead be, and I mean that we're talking a fully unlocked version. So 1480, because I'd imagine they'd have the same clock, 2 operations per second. Yeah, so this will give you about 13.2 teraflops of performance, which essentially, I mean, what this will mean for the, let's just call that the 1180, because that's what this will be. This will be your 1180, which will probably be what, like the $600 or $700 card. So yeah, essentially what you'll get for the 1180, what you'll get is what, that's just 1080 Ti performance. That's all that is. I mean slightly above. It's what plus 32% performance. That's roughly what you can expect from the hardware. I doubt they'll go with 16 gigabyte instead. It will be 8 gigabyte, but I'm damn sure they will actually go with HBM2. So as a note that That at the moment costs about $240 extra for 8 GB. That's at HBM2, by the way. Like, if you're like, well, how come they can give like an 8 GB card for like $200? It's because they're not using HBM2. They're using GDDR5. Now, for GDDR5, I think 8 GB at the moment costs about $160, something like that. $170, something like that. It's not much, but this also means that that won't be 300 watts, but instead, what will that be? Okay. Mm-hmm, mm-hmm, mm-hmm. No, that's not right. Or is it? No. I mean, well, yeah, kind of. So that'll almost certainly be your peak, and then you're gonna expect that to be like 195 watt average. But yeah, I mean, they're gonna go with 610 instead of 815 for the simple fact, like, yeah, when you have a plate of silicon and say we've got a 12 centimeter plate, and that's usually what they're going to be um, working with. Well, you know, when you cut it up for printing the dies, you've got all of this excess around the outside that's just kind of wasted because they're not full dies. So you can only sort of you can only really count like the full dies as opposed to like this area. So what that leaves you with is this area in the middle. Those are going to be the quote unquote good dies. But the thing is they're still going to have individual sort of damage. The dice, so none of it's going to be very, very rare for any of these to be perfect. Um, but still, you're only going to get. I mean, from I'm not even going to bother with the math right now because I'm not in a math kind of mood, not to figure out areas and whatnot. But if we just say like, if we say for example like the 800 millimeter, I mean 12 centimeters square, technically speaking, say 120. Maybe? No, that seems big. No, that's centimeters, like... I don't know. In fact, let's make it easier. I'll just say this is 80 centimeters, and we'll call that nearest makes no difference 8 centimeters, because, 800 millimeters. So, we'll have 10 for every one of those. And we're just assuming square dies. Whereas, like, the 600 millimeter one, Yeah, it's 6 centimeters. You can fit more on, so 80 divided by 6 gives you what, 13. And then if we say like a good amount is like 1 in 10, so like 90% of them are good. This means one's bad there, one's bad there. You know, so you're getting away with like 9 and 9. The thing is that 80 centimeters, again, like just for argument's sake, we'll say that that costs like $5,000. And we're just saying it's $5,000 to sort of get the silicon, do the do the actual production, blah blah blah. Let's say nothing else costs anything extra. Well, in that sort of scenario, you're looking at $500 for the 815mm chip. And 416 the 610mm chip. So, you know, which one are you going to choose? You can produce more of them, and you can sell them for a bit more. Because obviously you can jack up the price. And as I said, like I think this is a massive overestimation. I think they actually cost about 66% of that, more than likely, and these aren't real figures. This is just an example, okay? Don't take this as this is exactly what's going on behind the scenes. I mean, it's a good approximation. It's not like 100%. Oh yeah, this is exactly what's happening, but you get the idea. So this is why they'll go with a 610mm instead of 800mm die, even if they can do it. Because that 800mm die, because they're getting so many fewer. And again, like, bear in mind, what we're basically talking about here is nearly a third to 20% fewer dies. In fact, I was completely wrong. I'm sure I was completely wrong when I did that. No, I was right. So, yeah, I know they're much cheaper actually. So yeah, you're getting sort of like 30% more or whatever that you can actually sell, and like, you know, it's depending on how many sort of good ones you can get away with. Depends on sort of like what kind of premium you can add to the graphics card cost. Because obviously these lower ones, if there's one that's sort of like, you know, half a dozen of it is just balked beyond belief, like that account for sort of the one that doesn't work. But then like if you've got one that has like maybe a couple of things, but it's not major, but it's enough to lower the thing, and you're just going, okay, well, that one right there is now like an 1170, because there's no way it's got enough cores in order to be an 1180. This is typically why the high-end graphics cards are as expensive as they are, by the way. Because like between the cost of the memory, which can be ridiculous, like the cost of memory, I know these are overinflated figures because I know full well the cost of memory, even at the high-end graphics cards, is going to be a minimum of 50% of the cost of that graphics card. An absolute minimum. Like with HBM, I think it's slightly over. So that's something to always keep in mind. I don't think there's anything else I really need to go over in consideration with this. Like there's no technology that essentially it's still Maxwell. Like this architecture, just like Pascal was, is still Maxwell. And while for all intended purposes, we're going to be seeing a sort of a 30%, 40% performance increase. So it's going to be the same as going from the GTX 980 Ti to GTX 980 to the GTX 1080. It's going to be that same performance gap between the 1080 and the 1180, which is good. I mean, this is definitely a fantastic performance increase. In terms of price, they're not going to be able to bring the price down anymore, because of the way that they're approaching this. I think what we're seeing with NVIDIA is they're reaching the tippy top of what they can possibly provide consumers in terms of performance without just getting bigger and bigger and bigger. And that's essentially what they're doing here. All of the performance and the power is going to come from this. It's going to come from being 12 nanometer instead of 16. And that's where all of the improvement of the GeForce 11 series is going to come from. Volta is going to be very good for deep learning scenarios or Bitcoin mining or just anything that realistically just uses like massive threadnoughts of data, but doesn't necessarily need complex calculations to be handled. You're just talking about it's just the sheer amount of predictable data that is going in, which essentially like an add and multiply is better known as a dot product. So it's used primarily for 3D positioning, sort of 3D positioning, comparison, that kind of stuff. It's there just to do so 120 teraflops of comparators is just great for like artificial intelligence, for example, where it's like, well, is this data okay with this data? Is this data okay with this data? And then you're just checking against the results. It's not great for data that has to be very, very fluid, which a lot of gaming stuff does have to be. So as I said, I don't see the Tensor cores being even remotely useful for gaming. I mean, there's going to be very, very select edge case scenarios, and you keep in mind that, like, for the RX Vega, yes, it's got the floating point 16 stuff, just like they've added now to Volta, which is going to be very, very good. One thing I should have probably showcased was, because they've disconnected these, into sort of two separate pipelines. This now provides the asynchronous support that they needed before. There's actually something about the thread warper that they were doing. I think I've got to, again, I've got to turn off writing to be able to show it. Where is it? Yeah. So they've changed how the threading works. So before, as you know, in the last video with Vega, I was saying how like it's just basically sequential. So it's just filling and emptying as it needs to. Whereas the new one is capable of accessing any one of 32 different threads. So we should be seeing sort of better asynchronous performance. They're not exactly clear on how they've done it, because it seems like they've just improved the multi-threading. In like it's how do I explain this? So like with this one, you've got the main thread that comes in, then you have the next thread, you have the next thread, you have the next thread, and they're always going to be in that sequential order. Whereas with this one, they have whatever thread's ready. So it might be this thread next, and then this thread, and then this thread. And so the sequential order is basically first come, first served, as opposed to first in, first out. So as I said, it provides better asynchronous performance, but it's not like fully asynchronous. Yeah, as they're showcasing, like they're showcasing that they're still synchronizing it. They're just allowing it to diverge. They're just allowing the threads to diverge until they then sort of synchronize them at the end again. And this is something to keep in mind, like they are still synchronizing all of the threads. So, yeah, this is how they previously have done it. So, I don't know, it's... As I said, I'm not... From a technology standpoint, Volta is incredibly disappointing. At least if this document's anything to go by, maybe they've changed this, maybe they've improved this now. But considering, like, I was also looking through the CUDA features, and they were still basically talking about the exact same thing. They literally are talking about the exact same thing. So it's and again, like here's where they were showcasing of just like, oh well, these are the performance uplifts over CPU, and you're like, well, okay, but I was expecting it to be faster than the CPU. Like that's not. If your latest and greatest GPU is not absolutely demolishing CPUs in terms of this performance, where a CPU has like four of these four pipelines, and your GPU has like what 128, if you're not demolishing the crap out of it, then there's a problem with that architecture. Still, I mean, like from a performance advantage, like from a gamer's performance advantage, we know, like I'd say, we know more about Volta. We know far more about what Volta is going to be, is just simply going to be. Um, as I said, like the speculations I'm making in terms of like the performance, the cost, etc. Yeah, no, it's 100. I 100% stand by them. I think the GeForce 1180 is going to be what, $700 at launch, like $600 to $700 at launch. I think it's going to have 8 GB of HBM2. Um, I think it's going to ship with a full processor capable of 4,480 CUDA cores. But I don't think it's going to have all of those unlocked. I think they're going to have 13 teraflop performance, and I think they're going to be sort of aiming for the 250 to 700 250 75 watt TDP. I almost guarantee that's what they're going to hit. And I mean, it's from a performance standpoint, that's 30% performance over what we're getting now. And you're going to see that across the entire range of the 11 series. But from a technical standpoint, it's just like, I mean, it's not. It's kind of like the concept. It's kind of like sort of talking about Maxwell to Maxwell 2.0 to Pascal and now to Volta. And essentially, we're still talking about Maxwell architecture. Realistically, this is still just Maxwell architecture. We're just up to revision 4, which now supports Tensor cores. And that's it. There's nothing. There's nothing that they're doing with this that is, you can sit there and go, oh, that's really awesome. That's really cool. Like I didn't think that's what they would be doing with the hardware. Whereas with RX Vega, you do have that, even though they're like, well, it's not going to be that big of it's not going to be that amazing in terms of performance. It's going to be good, but it's not going to be amazing. And now I've sort of I think I understand the two kind of quite well, at least on paper terms. Yeah, it's kind of like the difference between the GeForce 700 series to the GeForce 7 series to the GeForce 9 series to GeForce 10 series, and now the GeForce 11 series. And you're just like, they're just they're just better cards. Like they're nothing that's going to sit there and make the market catch the market on fire or anything like that. They're not going to change anything. They're just they're just the same card we've had for the last 4 years, with more cores, more clock speeds, better power for efficiency. It's the same goddamn architecture. As I said, like, I really wanted to be excited about what the Tensor cores were. I really wanted to be very, very excited about them, but they're rebranded technology that every single CPU has already. And I see the point in it. I see it being useful in a graphics processor or a graphics accelerator. I mean, I think having it as a separate chip is part of the a graphics accelerator makes far more sense than having it part of the graphics processor. But I mean, that's just me. Like, I just think sister boards would make much more sense in this standpoint. But I mean, the industry's moved away from sister boards, so. I mean, I think this would be more impressive. This would be more. This would be more incredible if the tensor cores weren't in the compute unit. If they weren't in the CUDA units themselves. If they weren't in the shader modules, and instead they were part of the SLI link. So they're doing the tensor stuff between the GPUs. I think that would have been special. That would have been interesting. But as it stands, they're not. So, I mean, take it for what it is. I think NVIDIA is going to have some very solid hardware, just like they've had some very solid hardware for the last, 5-6 years. But it's not. This isn't anything that is that exciting. I don't know. Again, comments down below. Let me know what you think. I expected something more. Something just. It's kind of like the latest Intel processors, where you're like, they're doing these changes, and even though like they still are technically ahead of AMD in many respects, because it's so tried and true technology, you're like, I don't give a fuck. I don't care. Like, it's what do you want? Do you want a fucking medal for being able to do exactly what you've done for the last couple of years and just slightly improve it? Like, it's not that interesting. It's good. It's good. It's fine. It's getting it's more performance year on year, but it's not breaking the mold. It's not doing something revolutionary. It's not doing something innovative. It's just more of the same of the old. And the thing is, I'm not even convinced that NVIDIA can get away with this. As I was saying in the RX Vega speculation video, even when we look at the review benchmark, should be out sort of like over the next couple of days. But even when we're looking at sort of like the Frontier Edition, for example, we're seeing something that shouldn't be happening. And that is under DirectX 9, under DirectX 11, under OpenGL. The RX Vega is it is performance-wise keeping pace with the GeForce 10 series. And it gets difficult to sort of explain how important that is, that 20 to 30% performance gap that was there in those APIs is gone, while we're seeing the exact same sort of performance metrics that we should be expecting from like DirectX 12 and DirectX 11 and DirectX 12 and Vulkan. So that to me is sort of fascinating, because it makes you really wonder, like, if now we can start saying, well, clock for clock, teraflop for teraflop, these are now directly comparable in performance. Even if they're completely different architectures, they're now finally comparable in performance, and I don't have to be sitting there going, okay, well, if AMD is getting like 12 teraflops, I have to then sort of multiply that by 0.8 just to get somewhere in the ballpark of what NVIDIA will be able to do in like DirectX 9 and DirectX 11. You know, it just, that's now disappeared, and so like it makes me really wonder what without any innovation on the architecture, what NVIDIA can really offer in the 11 series if the tensor cores aren't sort of this novel way of handling um, transistors. As I said, I was hoping for something as sort of like, oh my god, as HBM or HBC memory, but it's not. I don't know, as I said, comments down below. Let me know what you think, whether you're excited for Volta and Tensor cores, and you know, if you think it'll be great for NVIDIA. I think they're gonna. I think they don't even give a fuck about gaming. To me, this is what this looks like. To me, it looks like they don't give a fuck about gaming. What they now care about is the deep learning sort of server centers, cloud servers, stuff like that. That's what they care about. They don't. They don't care about gaming. Because if they did, there would be innovations this generation. They would be trying to compete with RX Vega, and they're not. As I said, I don't think they give a fuck anymore. What I think they're going to do is they're going to keep milking Maxwell until they're no longer competitive, and then just give up. That's what it appears like they're doing, and that's sad. That's very, very sad. So, I mean, as I said, I mean, it's just my opinion. Um, I'll leave comments. I'll interact and sort of continue the discussion down below. But I, I'm trying to be positive. I'm finding it really hard. I'll catch you guys in the next video.